So what is real analysis? First of all, it's not the opposite of fake analysis. Here, real analysis is the study of real numbers. And in particular, you may wonder, why is there no rational analysis? What is it about the real numbers that makes them so much better than the rational numbers? And in order to do that, let's first define the natural numbers. So you start with 1, and then inductively define 2, etc., etc. And this system that you get is what's called the natural numbers, but there's already a problem. You cannot subtract in the natural numbers. And that's why we need to extend our universe to include things like 0, -1, etc., etc. And this system is what's called the integers. Now, here's another problem, because in the integers we cannot divide by things. So 1/2 doesn't exist in Z. And that's why we need to extend our universe yet again to include the rational numbers. Just the set of fractions of integers. And what's nice about the rational numbers is that they form a field. And a field is just a system we can add, subtract, multiply, and divide. And in addition, no pun intended, in the rational numbers we can also compare fractions. We have things like a less than or equal to b. And what's great about this is that the rational numbers then become an ordered field. And now, here's the thing. Well, there's some numbers that are not rational numbers, like square root of 2. And by the way, 5,000 years ago, people believed all the numbers were rational, but then someone discovered square root of 2, and oh boy, did math go down after that. However, just because there's a number that's not rational doesn't explain why the real numbers are so much better than the rational numbers. Because there's also, complex numbers or quaternions. So why do we study real analysis here? And it has to do with something called the least upper bound, which is a generalization of the maximum. So let me first define what it means for something to be the maximum. So consider a set S. Then we say that M is the maximum of S. So M equals to the maximum of S if two things are true. First of all, the maximum is attained, so it is in your set. M is in S, and moreover, everything in S is less than or equal to M. So for all S in S, we have S less than or equal to M. Now, it's a nice concept, except it doesn't always exist. So, for instance, even in the real numbers, if you take the set 0, 2, so the half open interval, then there's no max here, because the max would be 2, but 2 is not in your set. So the question is there some way of generalizing the max in order for it to always exist? And yes, there is. It's what's called a supremum, or what's called the least upper bound. So in particular, consider a set S. Well, if let's say it's bounded, whatever that means, then it has many upper bounds. So here, for instance, is an upper bound, and which, by the way, is just a number that is bigger than all the numbers in that set. But notice here we can actually do better. Like here we have another upper bound that's smaller than the first one. And in particular, the supremum is what's called the least upper bound. So it's the smallest possible upper bound. And in some sense, it's a number that kind of nudges your set from above. And in particular, what's the definition? We say that M is a supremum of S if two things. First of all, M is an upper bound. Okay, for S. And moreover, it's the least upper bound in the following sense. So here's a small analogy. If you're not the best student, then there's a student who's better than you. So in other words, if M1 is less than M, then there is some element in your set, so there is some student that is bigger than M1. So there is S in S with S bigger than M1. In other words, again, it's the least upper bound. Anything smaller is not an upper bound. And the question is, does the supremum always exist? The answer is yes. It depends on where you're at. And here's what I mean. For instance, consider the rational numbers. So a lot of holes here. And moreover, consider the interval minus square root of 2 and square root of 2 in the rational numbers. Now, how can we write square root of 2 here, this interval here, without using real numbers or without using square root of 2? Well, it's just a set of all rational numbers whose square is less than 2. Now, this set, even though it's bounded above, does not have a least upper bound. Why? Because the least upper bound would be square root of 2. But it's not in Q. However, this is not true in R, and this is really what makes R so much better than the rational numbers. So R is what's called complete. Namely, every set in R has a least upper bound. So even the set with lots of dots, it would have a least upper bound, which is just square root of 2. And that would be the supremum. So in other words, the single most important thing that distinguishes R from the rational numbers is what's called the least upper bound property. Okay. In other words, any non-empty subset of R, if S not empty is if S is a non-empty subset, then supremum of S exists. In other words, any non-empty subset of the real numbers has a least upper bound. And here I include the case infinity, so we don't even need the assumption about bounded above. And again, not true for Q, but true for R. And it seems like such a small concept, but it's literally the thing that makes real analysis work. It's the big bang to the theory of analysis. See what I did there? And in particular, we can deduce other properties like the Archimedean property or the fact that rational numbers are dense in R. And last but not least, just a couple of remarks. We can also define the infimum of S, which is kind of the greatest lower bound of S, meaning that if, again, you're not the worst student, then there's a student who's worse than you. And also, we can define, we can extend the real numbers to include infinity. So we say supremum of S is infinity if no matter how big of a number you have, there's always an element of S that's bigger than M. And one more thing, there is a way of explicitly constructing the real numbers called Dedekind cuts. And there was a YouTuber that gave this amazing comment about this. He was saying, what is a real number? It's a way of dividing up, so real numbers, set of equivalence classes, rational numbers, of set of equivalence classes, integers, of ways of building up the empty set. So the natural numbers. And again, that's what makes them so great.